All right. If at any point you guys can't hear me, just let me know, okay? I don't think I'll be staying by the mic. Bonjour. That's probably the, I tried learning some French words. It didn't really go well. It's a real pleasure being here. Thanks, Rui, for inviting me, for hosting. Today, I was planning on giving a technical talk, and then when I understood I'm going to give the first talk of the day, I decided to maybe take a notch off a bit, talk a bit about more of a perspective talk, give you ideas of what you can do with some tools that I'm going to present. My name is Itamar. I'm currently freelancing. I'm contracting, doing a lot of work in the area of search. I've been working with search engines and architecture for quite a bit now. I've worked on RavenDB in the past, and now I'm contracting mostly on Elasticsearch and Lucene. And that field, as we're going to see today, is somewhat hot today. You can do a lot of things with it. It can solve a lot of problems. And it can also give you tools to do stuff that you might have not thought it could help you with. And that's basically what we're going to look at today. Hopefully, this session will help. I will be able to share with you the passion that I have for search engines, for data analytics, for those kind of things. And what my goal today is to show you how you can take raw data and make use of it, transform it into knowledge, into actionable knowledge, something that you can actually act upon and do a lot of really interesting things with it. Okay, so first of all, as Rui mentioned, there is this hashtag. This is the NCrafts hashtag. I'm actually currently tracking it, so we have a nice demo coming up in the end of the talk. So please tweet and make the demo even more awesome. And hopefully my software doesn't crash. And let's start with asking, what is data? I would be happy to hear thoughts from you. What do you consider as data? Wake up.
Information.
Okay. What is information? Think about a system. You have a system, right? What would be the data in your system? What types of data do you have in your system?
Business data.
Okay. Databases. Okay. Like what?
How the features are used. If you have different ways to use the same feature, which doesn't display.
Okay. Usage data. Sorry? Cache data? Okay. Any other ideas? Okay, so, sorry? Sorry? Logs, okay. So that, when people think about data, it's a lot of times they think about the actual business data, right? What your application basically works on to provide users with actual stuff, right? So if I'm LinkedIn, so that would be my users base, maybe my connections, the companies that I have on the database. So basically, it boils down to database rows, right? But that's not really the case a lot of times. Many times, your system just provides a lot of users with stuff, but the data is not that significant in your system. The usage is. And this is the guy that mentioned the usage metrics. So you can actually measure that and use that for data. So nowadays, companies are being sold for billions because they have a lot of users, but not only because of their user base, it's because the data that you can produce out of your users. Now, that doesn't mean that has to be illegal or in any way, but still, there are a lot of things you can do when people use your applications. And you can improve on your application based on that data. But you have to collect it. And that's what we're going to look at today. There's also a lot of public APIs. You can actually go to the web and search for public open APIs, and you'll see quite a nice collection of them. So for example, the UK has released the crime database. So whenever a police unit goes to solve for a crime, they log it, and you have access for that, and you can do a lot of nice things with it. There is logs. Quite about every application can output logs, but you can also output logs by yourself and use that, for example, to measure usages. You can track exceptions. You can actually, if some part of your system threw an error, you can catch it and save it and log it basically, and then use tools to analyze those errors. For example, if you have a really large system, you probably have many of those, so you need tools to work with that. So data is probably a very broad term that you can file quite about anything under it. And a lot of times we don't really realize what data we have access to. So before we start, it's really important to understand that you might have a really precious data in your hands, but you haven't really realized it yet. And all you really need is just good tools to work with that data. So everything is data. And our story really starts with search engines. Okay, that's also historically, and also because it really helps sort things in our mind. Can you guys, there is a lot of words. This is beer ipsum, the modern version of lorem ipsum. Can you guys spot the name of the conference here? NCrafts, somewhere. Good eyes. Good eyes. Okay, so it's really tough, right? I mean, you're down the bottom, and you have, like, I wanted to say, okay, you can't really do that, so here's an easier version, but you guys nailed it. So working with a lot of data as humans, or let's put it this way, reading data, okay, we do this in a very certain way, and using that way to search for stuff, it's not really easy to work with, right? So basically, when we read, we go from a document level to a word level, right? We basically go to a document, go to a newspaper article, and start reading it. And basically, we go word by word in reading that article. Now, whenever I want to search for something, so I want to find that document, that article, I'm going to use a word to find that article. But I cannot do that if my things are sorted on an article basis. So I will need to go to every article that I have and then go to every word in that article. So what search engines did, and we are going to look into that, basically they took that process, the reading process that we have, and inversed it, right? So you're probably familiar with that concept. Well, back in the days when we had books, you would open the book in the real part of it, and you just you would have an index, and you look up things based on word to find in which page they appeared, right? So that's basically the same concept. We inverse that process. Instead of reading, going to a document, and then looking at words, we will have something that tells us, okay, here's all the words I know, and for each word, here is the documents it appears on. We will see an example for that in a second, but the idea is that inversion process gives that a lot of power. It starts with the power of searching, of really, really efficient and fast search, but it goes a long way from there. And it doesn't have to be words, right? It can be numbers, it can be all kinds of entities, and that's basically where it all really starts. So this is also a story. It's not only a story about how we can take data, so in this case a lot of text, and try to make something out of it. It's also a story of an evolution of a software. And for me, it's a really inspirational story, because that search engine technologies, they exist for dozens of years now. I mean, the concepts exist for dozens of years. The modern search technologies started being written around 15 years ago, something like that. And as we will see, that software really evolved in a really, really interesting way. From search technologies, it got to a place where it's actually data analytics tools, and we can do really, really interesting stuff with it. So that's inspirational, at least for me. So how does search work? So we mentioned the inversion process. Let's see it in action. So let's say I have, okay, it's cropped. Let's say I have a bookstore. Okay, I'm selling books. And I have millions of books. Here is 4 of them. What I would do is I will take each book. I will have different properties for each book, and I will just throw each of those properties into that inverted index. So each book has, for example, this book, it has the title, it has the author, it has pages and a price, and all those books has that as well. And instead of going through each and every book and looking up the value once I want to find a book that answers a certain query, what I will do a process before even performing a search. I will do this process once, and I will take all of that data and throw it into some sort of, here it displayed it as a table, but it's basically a very efficient data structure that lets me look up values very efficiently. So those tables, basically each of them represent the inverted index for that specific field that I'm looking on. So for example, I have the book titles, author names, etc. And you'll see that it's sorted alphabetically. And that is a very important concept, because once it's sorted alphabetically, I can use very efficient data structure, Patricia, Radix, and look up those values really, really quick. Once I did that, I can start looking up things, right? So for example, if I wanted to find all the books with 400 pages, all I would have to do is go to the right table or right index, look up the value. If it doesn't exist, I know I don't have any such books. If it does exist, I just get the number of the book from it, and I can go and retrieve that book. Obviously, I can do stuff like ranges. I can let the index also tell me what the values are, so I don't have to explicitly ask for a specific value. I can just tell the index, okay, give me all the documents that appear under a value that starts with, for example. And basically this here opens up a whole lot of opportunities. So queries don't have to be really simple. They can actually combine different fields together. They can go and say, okay, give me all books with 400 pages and with an author name of Dan Brown. In this case, it will yield no results because the intersection is empty, right? I have 3 and 2 and 4, so no results. So queries, that structure really gives us a really good way of working with queries. I have a lot of power when querying. But that's really simple inverted index, because what I did here is just take the values, invert them, have them in a table, and that table is giving me good power for querying, basically. And we already know that from SQL Server and all of those other databases. Basically, they use the same technique. So what's special about search engines, right? Then we get to full text search. Now, what full text search does is take this concept and basically take it one step further, because instead of just having that large text or whatever thrown into the table, I can now do some pre-processing to that before throwing it into the table. So if previously I had author name of Dan Brown, for example, okay, so this is 2 words. If I'm looking for Dan Brown, I would have to look up like that. I would have to say, okay, give me all books by an author named Dan Brown. Now, I would have to specify the value exactly as it appears in the index, because computers are stupid, right? They do whatever we tell them to do. So I'd have to have this capitalized. I'd have to have the space, and so on and so forth. What full text search gives me is the ability to break down text and do some normalization and some processing. So for example, here is an example of one field. and I have 6 documents with that one field, instead of taking all of that value and throwing it into the table like we've seen before, what I'm doing now is I'm doing two steps before that. The first step is called tokenization. I'm taking that value and I'm breaking it down, in this case on spaces. I'm breaking it down into individual parts. And then I'm throwing those parts into this table. Okay? So I'm taking that concept that we had of inverted index and I'm now applying it into a word level of my value. Okay? And that's basically what we're going to see here. Now, that's only the first step. The second step, and here is how it looks enlarged. So whenever I'm going and actually searching for stuff, it's exactly the same like we've seen before, right? I'm going to go to that table, and I'm going to look up the exact value in that table, in my inverted index, basically. Again, very specialized data structure, very efficient, usually in memory. And so I'm going to the table, I'm looking for the exact value that I'm looking for. And the inverted index is going to tell me, okay, I know this value, and this value exists in 3 documents. And it will give me the numbers of those documents. And then I can go back to my storage, find those documents, and find the words in them. The problem is that those values are not necessarily normalized. What do I mean by normalized? That means that if I was looking for keeper, I will not find documents called named keep or keeps. Okay, and I need to take note of that, because maybe in my context those 3 terms are exactly the same, or they have the same meaning, or let me say this like that. I would expect to get documents with the word keep when I look for keeps, and the other way around. So my way of doing that is normalize those values. So instead of having 3 completely different terms in that inverted index, I will want to merge them together somehow. The way I will do that is using the second pre-processing step that I'm doing. So the first one was tokenization, was taking big value, breaking it down into parts, and having those parts indexed in the table instead of indexing that one large value. The second step is going for every such token, as we call that, or term. I'm going to do normalization. In this case, what I would want to do is some sort of English normalization. I will go and use some stemming technique to find a base form for those 3 terms and just index that instead of those 3 and have all of those document values for that specific term. Now, this is where it gets really complicated, because it really depends on language, it really depends on corpus, it depends on users, on queries, on a lot of that kind of stuff. And there is really no one way to have this done. But it's really important to understand that when you do search, you really want to pay attention to what you're doing. There are best practices for English, for every language, for French obviously. But you really have to test even the best practice and see that it really provides the value that you're looking for. Now, there is a lot of other optimizations that we can do, right? I can go and remove terms that don't mean anything to me, or at least score them lower. And that's what I did here. For example, those are called basically stop words. The practice was up to some point, the practice was to remove them completely from the index. Now there's some other ways to still have them, but prevent them from influencing the results quality, and so on and so forth. So I have a lot of things that I can do with those values to actually improve search and make, or at least make the search behave the way I want it to. That's the technical part of the talk. Let's see some code and make a check that we've been given a technical talk, right? So that's basically how it would look like, the entire process that I just described, how it would look like if I was to write it in code. Now, this is not a lot of code, but that's actually, pretty much what's being done. So this is the indexing part. What I would do is I will create some sort of a dictionary. That's my data structure, my optimized data structure that sorts things based on alphabetical order. And then I will go for each document that I'm going to index. And in that document, I will take the data. I'm assuming one field, okay, only one record of data in a document. And then I'm going to split it on something. Now, splitting, it's, again, my decision on what to split on, because maybe I want to preserve email addresses, maybe I don't, maybe I want to preserve IP addresses, maybe I don't, maybe I want to remove numbers, maybe I don't. So again, some sort of normalization is happening there as well, or at least decision making. So I'm going to split the text on something. That's called tokenization. And once I've tokenized, I have a lot of terms, a lot of tokens that I can work with. For each of those tokens, I'm going to do the normalization. Okay? And here I have some really stupid normalization. Trying to be smart about the plurals in English. And then I'm going to add that into the index. Now, not really complicated, not really too much work to do. But here's how the search looks like. Right? Because I did all the smarts, all the things that I had to do, I did it beforehand when I was indexing. So what I have to do now is basically take the term or the token that I want to query with. I have to put it through normalization again, because I want to make sure that my indexing and my search code basically intersect. Otherwise, I will not be able to find any results. And then all I have to do is look up in my data structure. So it's really simple. It's really optimized for reads, and it works really nicely. And this is how we get that performance that search engines can give us. It's not only that it's not only that the process that they do is faster and it's more logical and it's more optimized for the way that we really perform search. It's also because they do a lot of smarts behind the scene. And that code that we've just seen is implemented by numerous libraries or products. Now, those are open source. And my favorite one is Lucene. It's been around for about 15 years now. Written in Java, completely open source, really easy to work with, really flexible, really nice. Elasticsearch is the tree to the right. It's relatively a new product, a couple of years old, and what it does is basically it wraps Lucene and provides it with more power. For example, it allows you to scale out an index. It allows you to run against a cluster. It has a really nice query DSL and a lot of other things. So what I'm going to show you now, it's more targeted towards Elasticsearch and Lucene, but the concepts are really the same for all search engines. So the way you would use either of those libraries is you can have that in multiple ways, but the idea is usually to have that side by side with your data storage. Okay? That's a search engine. That's optimized to give you abilities to perform search. You would have that as a service or whatever side by side with your data storage and just replicate changes made to your data storage into the search engine. That usually would be the best use case. And the way you would use that, one way would be to use it as a search engine, right, to perform search. Now, what we're going to look at now is two routes into making knowledge or getting actionable knowledge out of raw data, as I said before. So the first route would be to perform search. It's a search engine. Let's use it for search. And what search really is a way for us to make sense of unstructured data, right? So up until now, up until recent years, we've been used to perform queries on structured data. So think about structured data as SQL database, right? Our data is basically structured. We have tables, we have rows, we have keys, we have triggers, I don't know. We have a lot of things that really help us understand our data and work with that specific structure. Now, the nice thing, or I don't know, the thing that complicates our data today, it's not only the amount of data that we have, it's also the format of that data. So we really want to be able to operate on a lot of data which is not really structured. If it's user content, or if you're building some sort of a crawler, you want to get web pages and be able to search on them, and so on and so forth. So search is really a great tool to make sense out of structured data. And let me explain. So for example, if you have a website, instead of giving the user a lot of menus and a lot of stuff that he needs to click and understand your site structure, maybe you can do something like say, okay, I don't have any site structure. I do have some sort of a search area where you can start typing things and I will be able to understand what you're looking for. Google basically did that for the internet, and it turned out quite well for them, right? So if you can have something like that for your for your application, for your website, just type something and I will understand what you're trying to do, and that's going to be quite neat, I think. And search can help you do that. Search also does something nice about the actual data that it processes. It doesn't only store those words or terms as we've seen. It is also able to rank results. So if you search for something, it will give you the highest scoring result at the top. That's most search engines will work well like that. It uses some sort of formula. There are a couple. The most commonly used one is called TF-IDF. And those formulas basically know how to rank results based on appearances of the terms that you use for query compared to the frequency of those terms in the entire index. So that basically means that whenever you search for something, you get documents that really, really, really are top scoring amongst all other documents in a corpus. And you can leverage that scoring thing to give users not only results, but better results, or the results that we're looking for. As I said before, search doesn't only end in finding text or finding values, you have actual values you can feel and see. Search has been taken to completely different places. So, for example, we have Geo-spatial search. So you can take a shape and you can find other shapes with it. So for example, think about a restaurant search type of application. So each restaurant in your database or data store or application or system is going to have coordinates, right? It's going to have a place in the map. Now, if I wanted to find all restaurants within a range of 1 kilometer from here, what I would do is I would issue a query using a circle, right? What I'm doing is basically, this is my current position. This is my point on the map. I want a radius, so basically I'm creating a circle with a radius of 1 kilometer from this point. So what I would do is basically I will index points on the map, and I will issue a circle query. What I can do even more than that, I can actually index polygons, more complex shapes, not only one point, but many points, and I will index those polygons, and I can use other polygons or points or whatever to query for those polygons. I can define even the interaction that those shapes are going to have, whether it needs to contain it needs to intersect, it needs to be disjoint. Okay, so the way we don't have much time to go into how does that actually works, but the idea is that we just found a way to represent shapes in a searchable way. Basically, we put into the index, for each shape, we put into the index several terms, and those terms are searchable using the same representation when used for query. So if you recall about tokenization and term normalization, that's basically taking that to the extreme. That's not the only usage that we can do. So you can't see the links down there probably, but we can even use it for image search. So I can take an image using some sort of formula and some sort of some logic or an automatic process. I can tag the image with various criteria. For example, the color template, the color palette that it has, right? So once I tagged it, I can use the same tagging mechanism to perform search. And to be frank, actually, the image search thing, I gave you 2 examples for it in 2 links down there. They're open source. They work. You can go and see how it works. It's actually not that simple. There is some formulas and some really interesting stuff going on there, but the idea is it's possible, and it's not even too hard to implement. So search really gives you a way to find data using, using automatic tools, not putting too much effort into it, only after only some initial drive to build something, and then you're basically done. You don't have to have editors and people to tag stuff for you. You can just use that. Now, what we can also do, we can also use various techniques to structure the unstructured, right? So instead of saying, okay, my data is unstructured, just search for it, which is good. I mean, it works. It's perfectly fine. You can actually even automatically try and structure your data. So I mentioned the scoring mechanism, term frequencies. We can use that model, for example, to find similar documents. So instead of having, again, editorial team tag documents for us and say, okay, this document related to this document, and so on and so forth. If, for example, I have some sort of a library or Amazon to offer similar products, what I can do is I can use what's called the bag of words model. And that bag of words model basically means, okay, I have this document. I know this document has those words. I know that document has those top scoring terms, words. I can use those terms to create a query. And that query is my bag of words. I'm going to use it as a vector to find, as a query, vector query, to find other documents that have the same characteristics. And this works every time, right? I mean, assuming we have proper indexing put in place, it works every time. You get similar documents. If you use that on a document talking about Paris, you will find other documents talking about Paris, because with all due respect, Paris is not the top scoring term in English, right? Other methods you can use is NLP, entity extraction. That basically means I'm going to look at the text, if we're talking about text documents, and I'm going to look at the text, and I'm going to extract things that I know are important, or at least their characteristic tells me they're important. And this is a way for me, for example, to find names of people. I can find places. I can find a lot of those kind of stuff. And in many applications, that's actually what I'm looking for. I'm not looking for verbs. I'm not looking for prepositions. I'm looking for names and places and stuff like that. So that's ways for me to structure data, even though I don't know anything about it, optionally. I can also, because I have that index, and that table actually contains all the data that I have, right? All the terms and everything. I can use it to perform stuff like auto-completion, search as you type, suggestions, and correcting spelling mistakes automatically. I can do all those kinds of stuff really, really easy. But that's not the only thing I can do. Now, what I did up until now, I used those values, right? The thing is that I can actually go and use the values to the right. So instead of using the terms for, I don't know, for auto-completion, for search, for stuff like that, and then just look up the occurrences that I have, I can use the occurrences themselves, okay? So what that means, for example, just by looking at this table, I can see that Dan Brown is the most popular writer in my library, right? Because he has 2 books, while all the others have 1 book only, right? So just by looking at this table, I can gain quite a lot of insight. And that's basically what the second route is all about. It's about aggregations, it's about looking at that occurrences table and trying to make sense out of it, or trying to gain insights by looking into it. Now, my indexes are not going to be as simple as the one that we just saw, but there are tools to make this even easier to work with. So we all know, we actually use this every day, probably. That's originally called a faceted search. That means that whenever you perform a search, the search engine is going to look at that table and do some really interesting stuff, but the idea is that it will show you the results, but it will also be able to break down the results into buckets, let's call them. So you would look at the results, but it will also be able to break them down for you, and it will tell you, okay, so you have those results, but you have also this breakdown of categories within the results. You can get breakdown and counts based on price ranges and days and I don't know, ratings and time it's been in the system, and so on and so forth. So that's called faceted search. It's quite a known technique for quite a while now. But the thing is, that's only where things started getting interesting. So search engines is the mechanism of going and indexing stuff in a very efficient way to search for it, and I just showed you how you can leverage that to actually gain insights from data using really nice techniques. But this is some sort of an evolution on top of search engines, that once people realize they have all of that information, they just started using it. And there's all other respected websites that we use today use that feature, right? eBay, Amazon, LinkedIn, whatever. All of those websites are using that feature. So it's quite standard nowadays. The thing is, faceted search, which is an evolution on top of search engines, basically is just the first step, because once people realize the power that it gives us, they just built on top of that even better frameworks. And what I'm referring to now specifically is the Elasticsearch Aggregations framework, which is, it's still being built, right? But there is a first version, very good version out already. It's basically facets on steroids, and you can do a lot of things with it. I'm going to show you just a bit in a second. And we can do a lot of things, and it's better to see that in a bit. It not only they give you that, the abilities for counts and stuff and working with numbers, you can actually, everything is happening real time. Because the way facets work, because of the way aggregations work, everything is in memory, usually. And because everything is in memory and everything is really performant, everything can be really fast, and as soon as data comes in, you can perform those operations on it. Now, you can instead of only using numbers and stuff like that, you can use a lot of built-in stuff that the search engines has. For example, this picture shows aggregations using Geo-spatial clustering, or using the geopoint facets. So I can also see counts spread across a table, across a map. And I can do a lot of other stuff. I can even do percentiles. I can do cardinalities on numbers. I can do a lot of really, really interesting stuff. What I do advise you to see this in action in a really, really cool demo. Mark Harwood, one of the Elasticsearch developers, has a talk called Uncommonly Common, revealing the uncommonly common. He uses all of those kind of stuff to perform really, really nice operations and really gain a lot of insights using those metrics, let's call them. I recommend you watch the talk. And the tools that actually work with Elasticsearch to provide you with all of that is Logstash and Kibana. Now, Logstash is a way to put data into Elasticsearch, and Kibana is a way to visualize and make queries out of Elasticsearch. And I'm going to show you a quick demo with that in just a bit. And before we do, let's talk about logs. So quite about everything is data. That's what I started with, right? So an HTTP server, an Apache web server, for example, will output something like that. Now, that's just one line of text. But if you can look at that, there is quite a consistent pattern here, because that's what logs are all about. So it's really, really easy to parse it out, right? I know this is the IP address. I know this is a timestamp. I know this is the path. And I know this is the HTTP code, et cetera, et cetera. So I can quite easily go through those logs of the HTTP server in this example and parse out those things. I can then take, after parsing, I can create some entity out of it, push it to whatever tool I'm using, for example, Elasticsearch, and that's what Logstash does. And once I have it there, I can use all of those aggregation techniques that I just showed you, and I'm going to show you in a second a real demo. I can use them to gain insight. So for example, if it's an HTTP server, I can understand usage patterns straight out of my HTTP logs. If I have a search page, for example, I can use that to log the actual queries, right? And do a lot of interesting stuff with them. I mentioned before, I can also use that technique to track down exceptions. So here is a .NET exception, right? An exception thrown for .NET. That exception is pretty much structured, right? It's not a one-liner, okay? It's a couple of lines, but it's still very easy to parse it out. It's very easy to persist that data. I can push it again into, for example, Elasticsearch or whatever other tool like that, and I can use that to monitor and to understand what's going on in my system. So I can do it both ways. For example, I can also output logs from my application. I don't have to take logs from an external source. I can go to my application. I can add debug or traces or whatever, right? And I can log those things and push them into Elasticsearch or whatever. And then I can go and do aggregations on that and track usage, track whatever. And if for example, one day something happened, then I will see some sort of a decline, right? I will expect some usage pattern. I will expect, I don't know, 100 such rows in a minute. And one day I'm just getting 50. Then I know something is wrong. Okay, so even if I don't look exceptions, I can use that to understand that something is wrong and use that to debug it. It's really, really easy it's really helpful when I'm dealing with distributed systems, because I don't have one entry point to the system. So I can have all of my nodes output those logs, index them across all my cluster, and have one endpoint I can access to view those logs. And then obviously I can also add the exception log in here into the same technique and analyze those exceptions in addition to the actual usage logs. And then I can also see a decline, and I can see an exception right in the middle of the decline, or right in the start of it. So let's sum it all up. Data is everywhere in your system. It might be even something that you haven't realized is data. So that's usage patterns, that's logs of quite about everything. Storage space is quite cheap nowadays. Just don't throw anything, just index it. You'll probably find a use for that later on. Data is also data that currently you maybe cannot work with, but once you start using search engines and you realize how easy they are to work with, you will be able to come up with really interesting ways of leveraging your data and giving your users a much better experience. And those logs that I mentioned are really, really good for deciding on a baseline for your system and tracking that performance and making sure it operates on a normal basis and finding optimizations opportunities and so on and so forth. I'll take questions, but before that, I wanted to show you a really nice demo. Yeah. So before the talk started, I started tracking. This is real-time tracking of, oh, sorry. Second. Yeah. Okay, so this is real-time tracking of Twitter. This is Kibana. Okay, this is the Kibana dashboard. I have Elasticsearch. Let me show you. No, okay, it doesn't want to go. Okay, so I have Elasticsearch running, and I'm running Kibana. Kibana is just HTTP JavaScript thing, HTML JavaScript. And I'm serving that from a local web server I have, and it communicates directly with Elasticsearch and does everything. And I have another tool running, pushing data into Elasticsearch. So what that tool does, it goes and tracks Twitter for certain keywords. I just wanted to generate some traffic, so I used Syria, Turkey, and Elasticsearch, Windows, and NCrafts. Okay, so you can see the visualization here, right? So this is in green, that's all queries, okay? That you can see that here. The queries are defined here. So green is all queries, and then we have the pinned ones, which is some sort of a red. It's NCrafts, and we have Elasticsearch in bluish, and Windows in orange. And you can see it plotted here, right? This is an histogram. You can see the dates. It's auto refreshes every 5 seconds from an hour ago until about now. And you can see it plotted. So green, bluish, red. This is the NCrafts one, and orange. Okay, and everything is real time. So I can see the hashtags. I created this dashboard to show some Twitter user statistics. So here, all the hashtags that being used count by counts. So Turkey is the most, Syria. I can see a map of where tweets come from. Again, live, right? So if a tweet has geographic location, I can see that it's clustered. So, for example, it's coming from, what's that? I don't know, London. It's coming more from here and a few from there and maybe one from here. Again, I'm faceting on a language, so you can see most tweets are in English. This is the most active users at this point, and this is the actual data, right? So I edited it. So this dashboard I built myself. It took me about, I don't know, 10 minutes to build. It's really, really easy. That's the point of Kibana, basically building dashboards for easy querying. And what I can do now is I can deactivate those other queries and stay only with the NCrafts one. And we can now see, let's do this. Let's see, whatever. So this is when I started it, right? So, okay, the color choice wasn't the best one that I made today. I could start at about 9 a.m. and that's, yeah. And up until now, and it's still refreshing. And we can see that the tags that are being used, obviously NCrafts is the most popular hashtag, but we also have those. We can see the users that actually made this, so whoever that is, well done. And obviously, by the way, there may be users that don't display it because I'm only taking the top 10 or something like that. And here's the map. I mean, all tweets are coming from here. I wonder why. And most tweets are in English, and this is French. I can do a lot more, right? I can go here and do add panel and add panels, and those panels I'm going to configure them in a few seconds. And I'm going to gain more insight. But I think that's really nice demo showing all the power that you can do. So tweets are quite, quite easy to work with maybe, but even your system, I'm sure there's a lot of room for doing stuff. Okay, that's about it. I hope you enjoyed it. And if you have any questions, I'll be happy to take.